Welcome back to our lesson on perpendiculars, and in this video I'll show you the construction and the proof for dropping a perpendicular. So first let's look at the construction. And the idea here is that we have some line. I'll just draw it actually at a little bit of an angle here. And then we have a point that's not on the line. So I'll just draw it up here. And the idea is we want to draw a line through this point that's perpendicular to this line. This is called dropping a perpendicular because we're drawing the perpendicular line from this point down to this line. Now the first step in this construction is to set our compass to be, first of all, center it at that point and then set it to be a bit longer than the distance from the point to the line. And once you set it to be a bit longer than that distance, you can draw an arc like this. Make sure that arc intersects the line in two different spots. If the arc goes past the line, you can just extend the line. Now that we have these two intersection points, we need to make a perpendicular bisector of that segment. And the way we can do that is just set the compass to be this length, or you can set it to any length that's more than half of the distance. And there we go. And there we go. Now we line up the straight edge so that it connects this point, and this point. You actually just need two of the points, but I like to include all three in general to try to make it as accurate as possible. So it's this line right here, but the part that we're really interested in is this right here. Drawing this line from the point down, I'll draw the rest of it in a little lighter, but drawing the line from this point down to here, and there is our perpendicular. So that's the construction. Now keep in mind that because I set the compass to be this length, if I were to draw these two triangles, those would be equilateral triangles. So when I do my proof, I'm going to use that fact that those are equilateral triangles. So now that we've done the construction, let's look at the proof. So now in order to set up this proof, we need to have a line, and I'm going to go ahead and label this line AB, and then some point that's not on the line. And so that's my given. So my given is a line AB and a point P such that P is not on the line AB. My goal is to draw a line perpendicular to AB through P. So a line that goes through the point P and is perpendicular to AB. And as we saw in the construction, the first step is draw a circle centered at P that intersects AB twice. So it has to intersect this line here in two different places. You can always extend the line AB if you have to. So, and that does follow one of our rules. We do have a rule about extending. All right, so let's go ahead and I'm just going to draw this arc in here, make it just a little narrower. Okay, so there is my arc. It's not the full circle, but it's part of a circle. And so now I'm going to define these 2 points here. And those will be points, let's see, C and D. My justification, of course, for drawing a circle centered at P with whatever radius I want is rule number 4. If we look back to our, let me find it, our axiomatic system, rule number 4 says I can draw a circle centered at any point with any radius. And so that's what I've done. And then, of course, rule number 1 says I can draw or define a point anywhere I want. So that'll be our next step. Step 2, define the points C and D at the intersections. And that, of course, is rule number, I'm going to actually run into my, I want to save some space here because I'm going to be drawing an equilateral triangle here in just a moment. So probably right around there. Okay, so this is rule number 1. All right, now step number 3. In this step, I'm going to draw an equilateral triangle on CD. So I'm going to construct equilateral, this is short for equilateral triangle, CDE. Such that E is opposite P. The idea is I want to make sure, just because I could run into trouble, wouldn't necessarily, but I could run into trouble if these 2 points were on the same side. So I want this point on the equilateral triangle, this point E, to be in the opposite side of the line from P. Okay. And I'm going to go ahead and just draw in my equilateral triangle so I have everything I need in my diagram. Okay, what is my justification here? Well, right here, brick number 2 says I can construct an equilateral triangle. Okay, so that's brick number 2. Now I also want to draw lines connecting P with C and PD. So let me draw those lines in as well. And so that'll be step 4. Draw PC and PD. And our justification for that, rule number 2, says I can connect any 2 points with a line. All right, now that I have these points, I can specify, I can point out here that the length PC is equal to the length PD by the definition of circle. Also, the length CE is equal to the length DE, so I'll indicate that. And actually, I realized I want to draw one more line here too. I want to draw this point, this line from P to E. Okay. So I'll draw that line in there. I'm going to add that to step number 4. So I draw the line PC, PD, and then PE. Okay, so let's go ahead and write step 5. PC equals PD. That's by the definition of a circle. But also CE is equal to DE, so I'll add that here too. CE is equal to DE, That's by the definition of the equilateral triangle. Well, I know that PE is equal to itself, and so now I can say that step 6, the triangle PCE is equal to the triangle PDE. And therefore, this angle here is equal to this angle right here. So angle, let's see, this would be CPE is equal to the angle DPE. And that's by side, 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 right? So because this side is equal to this side is equal to this side, and this side is equal to itself, these two angles must be equal. Okay, let's go ahead and define, I should have defined that up here, but let's see, I'm up to point F. So I'll write that under here, and F. I don't want to write a whole new step right now. But I do want this point here to be defined, because now that I know that these two angles are equal, I can do another triangle equality. I can say that triangle PFC is equal to triangle PFD is equal to triangle PFD. How do I know these two triangles are equal? Well, side equal to side, angle equal to angle, and PF, of course, is equal to itself. So side, angle, side equal to side, angle, side. Therefore, those two triangles are equal. Since the two triangles are equal, these two angles here, which are part of those two triangles, must be equal. So, and angle PFC is equal to angle PFD by side, angle, side. Okay, so at this point, if you recall in the previous video, let me find it, I had gone through some steps in my proof for the line bisector. I had shown that, well, since these two are equal, and they add up to a line, they must equal 180. So since they add up to 180 and they're equal, they must both be 90 and therefore perpendicular. So these three steps right here. But I was thinking about those three steps and I was like, wait a second, you know, I remember studying Euclid's Elements and I don't remember that sequence showing up or that being a brick. And so I thought I'd consult Euclid to see what he would say about a situation like this. So let me pull out, hang on. So here's my copy of Euclid's Elements. I highly recommend it. And let's find out what Euclid's definition for perpendicular is and for the right angle. All right, let's see, where is it? Here it is. So definition number 10 says, when a straight line is set up on a straight line, makes the adjacent angles equal to one another, each of the equal angles is right, and the straight line standing on the other is called perpendicular to that which it stands. What this is saying is that if you have two lines like this that intersect in a way that make the adjacent angles, these are adjacent angles, equal to each other, then those two lines are perpendicular. Okay, that is the definition of perpendicular according to Euclid. Now it might feel like Euclid is sort of sneaking a brick into a definition here, but at this point we're going to go ahead and say, you know what, Euclid said that as the definition, we'll go with it. So now that we see that these two adjacent angles are equal, we can go ahead and follow up with step number 8 and say that this line here, PE, is perpendicular to this line AB, and that's by the definition of perpendicular, according to Euclid. So that doesn't mean that the previous proof that I had, wherever it was, I'm losing my track of the pages here, doesn't mean that this proof is incorrect. It's just different way of looking at sort of the same thing. So you could go through these steps, or if you want to go with Euclid's definition of perpendicular, then you could just say, since these two adjacent angles are equal, then those two lines are perpendicular. Okay, so let's go ahead and add this brick to our axiomatic system. So this will be brick number 6. And I'm running out of space to put these things. Maybe I will put brick number 6 over here. So brick number 6, drop the perpendicular. And let's think about, what does this depend on? Well, it doesn't depend on the perpendicular line bisector. It doesn't depend on the angle bisector. Really, the only brick that we see show up is brick number 2, construct an equilateral triangle. Other than that, it's just the rules and these assumptions and definitions. So let's go ahead and draw an arrow here. So it depends on brick number 2, and so yeah, so that's where it fits into our axiomatic system. That wraps up our lesson on perpendiculars, but remember, if you want to learn, you need to do the practice, okay? Practice problems will be in the description. Thank you for watching, and we hope to see you in the next video.